Quantum simulation shows how universe-destroying bubbles could grow. Physicists are finding new ways to model false vacuum decay, a terrifying, albeit remote, cosmic endgame. The good news is that you and everyone you love will die long before it might happen. Now, for the bad news. Someday, in the far distant future, eons beyond its 13.8 billion year adolescence, the universe could suffer a false vacuum decay. This would involve a bubble of incomprehensibly destructive power that would spontaneously materialize and ripple through space-time at the speed of light. Such an event would rewrite the fundamental laws of physics and obliterate our reality in the equivalent of a cosmic cut and paste command. Whatever was in the false vacuum, so this would be us, would disappear immediately right when this bubble spread through us, says Jakob Vodeb, a physicist at the Jülich Center in Germany. For decades, theoretical physicists have wondered whether the universe is stable or metastable. In the latter scenario, it is in a false vacuum that will eventually decay to a state of lower energy, a true vacuum. Vacuum, in this case, refers neither to an appliance nor to outer space, but to a state of truly empty space, which can still have energy even when it is devoid of particles. In recent years, theorists' experimental colleagues have begun tinkering with quantum systems to whip up analogous systems in the lab, given that working with bona fide universe-annihilating bubbles would be a bit dicey. Earlier this month, Vodeb and his colleagues published the findings of their cosmic bubble simulation in Nature Physics. Using a 5,564-qubit quantum annealer from the company D-Wave to essentially create a one-dimensional chain of highly sensitive magnets that could point up or down, they simulated the growth and interactions of cosmic bubbles. The researchers first arranged the qubits to point up and then tuned a magnetic field so that pointing down was energetically favorable. Over time, some qubits flipped to point down, and the flips cascaded to nearby qubits, forming clusters or bubbles. The analog bubbles then grew and merged, matching predictions about their cosmic counterparts. The results, first shared on the preprint server arxiv.org in June 2024, represent the first time cosmic bubble interactions have been simulated on a quantum device. This is one of the simplest demonstrations of how a vacuum can decay in a real, physical system with a proper analytical theory behind it, says Rupayan Ghosh, a theorist at University College London, who was a peer reviewer for the paper. That's why I think people should find it interesting. Contrary to their apocalyptic subject matter, the physicists who study false vacuum decay are rather zen about the whole thing. I don't really, live in existential fear, Vodeb says. So long, and thanks for all the flash frozen fish. To understand the meta-stability of the false vacuum, start by filling a bottle with distilled water and putting it in your freezer for a couple of hours. The bottle's water, free of dust or chemicals to trigger crystallization into ice, can remain liquid below the normal freezing point. This is a metastable state. Jostling the bottle will cause the supercooled water to immediately freeze to ice, shifting to its stable state. Another example of metastability, more morbidly apropos of universe-ending bubbles, involves fish. The Greenland cod, Gadus ogach, is a tan-colored fish that's uninteresting, save for the fact that its blood freezes at about minus 0.7 degrees Celsius. During the winter, seawater in their geographic range is colder than that, reaching a frigid temperature of minus 1.9 degrees Celsius. The cod are no warmer, but they swim along fine, unless they are brought into contact with ice. Researchers studying the phenomenon in the fjords of northern Canada in the 1950s placed the fish on ice and watched. Ice crystals surged across the cod's skin, rapidly killing the fish. Anne. Whereas flash-frozen cod are a classical phenomenon, false vacuum decay requires quantum tunneling, in which a highly improbable fluctuation takes the universe to a different state. How improbable is that fluctuation? If the universe is in fact metastable, recent calculations of vacuum decay have put its lifetime at about 10,790 years, a number so large that you could wait another 13.8 billion years for the arrival of a better analogy, and cosmic annihilation would still be 10,790 years away. Supposing you are fortunate enough to be around for a false vacuum decay, physicists have deduced that there is additional encouraging news. As a consequence of this rapid expansion, if a bubble were expanding toward us at this moment, we would have essentially no warning of its approach until its arrival, wrote Sidney Coleman, a theorist then at Harvard University, in a 1977 paper. Lacking a universe in a bottle to observe, physicists have learned to blow bubbles in a variety of media. A quantum annealer is slow and not very useful for computing, Vodeb says, but its thousands of qubits are ideal for such a simulation because they're very controllable, allowing bubble formation to be easily initiated and observed. Last year, Alessandro Zenassini, a physicist at the National Institute of Optics, and his colleagues at the University of Trento in Italy reported their observations of a bubble in a collection of about 1 million sodium atoms that were the size of a poppy seed and cooled to nearly absolute zero. In that case, the bubble consisted of clumps of thousands of atoms that flipped their orientation to emulate the shift from a false vacuum to a true one. Although such atomic clumps are closer to the conventional image of a bubble than the annealer's qubits in the new study, they are still only a crude toy model of the universe. Notably, they lack any meaningful inclusion of gravity. We cannot say anything about the real universe based on the 2024 experiment in Italy, says Alessio Riccati, a theorist at the National Institute of Optics and a member of the group that conducted that earlier study. That, of course, raises a broader and somewhat important, albeit non-urgent, question. Is the cosmos actually metastable, distantly destined for extinction by cosmic bubbles? Could be, Zenassini says breezily. Who knows?